Hi, this is Pat Kaplo. I'm solving problem number 38 on page 163 in the Giancoli textbook. The problem reads, a projectile is fired at an upward angle of 45 degrees from the top of a 265-meter cliff with a speed of 185 meters per second. What will be its speed when it strikes the ground below? And it says use conservation of energy principles. So in order to solve this problem, I'm going to start by first making a quick sketch. The sketch is going to look something like that. So you'll see that I've kind of prepared that. There's a little cannon kind of firing something here. You can see that this angle here is about 45 degrees, although we'll find out that that's kind of trivial. It's not consequential with the way we're going to solve this problem. I strongly recommend that you continue to use the bucket analysis. So we can say if I use red here to draw my buckets, I can draw a bucket here at this point, and I can say that the amount of energy in that bucket must be equal to the energy that I have just when the cannon strikes the cannonball strikes the ground. What kind of energy is in the bucket at point A? Well, it's two different kinds. It's a mixture of kinetic energy, because the ball leaves the cannon with a certain velocity, so it's got kinetic energy there. And it also is going to have some gravitational potential energy. We'll color that with green there. So we'll say that the gravitational potential energy at A plus the kinetic energy at A. And then when it reaches here, down here at point B, we can say that all of that energy has been converted completely to kinetic. So it's got kinetic energy only at point B. If we assume that this is our zero reference point, we know that the height of the cliff is 265 meters. So we're looking something like that. All right. If we write this as a conservation of energy problem, then we can easily just say that the bucket at A must be equal to the bucket of B. And that's what we're going to do. We're going to say that the kinetic energy at A plus the gravitational potential energy at A are equal to the kinetic energy at point B. At this point now, it's just some record keeping. I'm going to go ahead and expand each term. I'm going to get 1/2 mv squared at A. That's the kinetic energy at point A, plus mg height at A. That's the gravitational potential energy at A, plus 1/2 mv squared at B. This is going to be that huge amount of kinetic energy that I have at point B. Notice that I have a mass term in mass occurs in each of these terms. Therefore, I can divide both sides by mass, and the mass drops out. And I'm going to get something that looks like this. 1/2 the velocity at A squared plus the gravitational acceleration times the height at A. And I'm going to multiply that entire term by 2 in order to eliminate it here from the right-hand side. That's going to be equal to V at B squared. At this point now, I just need to take the root of both sides. So I'm going to get root 2 times 1/2 V at A squared plus GH at A. All of that's going to be equal to the velocity at B just before it strikes the ground. Now in this last step, all I need to do is substitute. So I'll go ahead and put in my numbers. I'm going to get 2 times 1/2 the velocity at A. Now the velocity of A is given to me. It's this huge number, 185 meters per second. So 2 times 185 meters per second. Now this whole term, this whole piece here needs to be squared. So I need to put that in parentheses, plus 9.8 meters per second squared times the height at A. And the height at A is, of course, 265 meters. All of that's equal to the velocity at point B. Once I put all those numbers in, and make sure that you're giving some consideration to order of operations, you're going to get some large number. And when I did that, I got something on the order of about 200 meters per second, 198.5. Once I truncate for significance, I'll call that 200 meters per second, and I'll call that second zero significant, is going to be equal to my velocity at point B just before it strikes the ground.